Now, if you've played many escape rooms or other puzzle games, you'll be familiar with the idea that letters can be represented as numbers, where 1 is A and 26 is Z. And also that numbers can be encoded in binary format. So the pattern 00101 is the number 5 that corresponds to the letter E, for example. And this project is all based around those ideas. So here I've got an ESP32 that's powering this LCD display, and it's also got this box on the front that's got 5 laser diodes on the top, and those are pointing directly at 5 light dependent resistors on the bottom. Now over here I've got a series of wooden cards that have got holes punched into them, and those holes are punched in one of 5 positions corresponding to the layout of the diodes and the LDRs underneath them. So what happens if I pick a card and I push it into the slot? It's going to obscure a particular pattern of lasers from hitting the light dependent resistors underneath them. That can be detected by the ESP32 and interpreted as a binary value, and then that can be mapped to a letter, for example, or it could be used to uniquely identify an object. The cards themselves are very simple wood with some 6mm holes drilled into them, and if you have 5 lasers, as I do here, you've got the possibility to encode 32 different values. So here's another example, and this time it's running on a humble Arduino Uno. As before, I've got an LCD display, and I've also got my 5 laser diodes which are pointing at 5 light dependent resistors. And if I just sandwich those two together, you can tell when they're lined up because you can actually see some of the laser light diffusing through the base of the LDRs there. Now I want to make sure that you can see the output from the LCD display, because this time, instead of encoding just a single character value on the card, I've made a wheel that encodes an entire message. So around this wheel there are 8 sectors, and each of those sectors has 5 different segments that can either be cut out or filled in solid, which again correspond to the 1 and 0 values of a 5-bit binary code. Now if I insert the wheel into the reader here, and then as I rotate it clockwise, I want you to look at the output from the LCD display there. So we see the letter M comes up to start with, then E, and hopefully you'll be able to see the message appearing. I'm afraid I do literally mean the message appearing. So these sectors encoded the letters M, E, S, S, A to E, and then this final sector here, which has got all 5 segments with holes in, that's kind of like a reset which I've put into the code. So that will blank the screen, and that's equivalent to if the disk wasn't there at all. Now let me give you some more information about the components I'm using and how they're wired together as shown in this fritzing diagram. So if I start with a quick overview of how everything is laid out, I've got my array of 5 laser diodes here, which are each pointing at a corresponding light dependent resistor. Now those LDRs are connected to a microcontroller. In this diagram I've depicted an ESP32, but this will work just the same with an Arduino, a Raspberry Pi, or any other microcontroller, so long as it has at least 1 analog input pin, 5 digital outputs, and also an SPI interface which is going to be used to control the LCD screen here. So now let's look at each of those systems in more detail. So we start with the array of laser diodes. Now I'm using the very cheap, readily available laser modules you can buy on eBay and Amazon, things like that. And I've connected them in parallel to this 5-volt DC power supply here. Now normally if you wire an LED into a DC circuit, you need to include a current limiting resistor in series with the power supply. But the laser diodes that I've bought here actually have a built-in 91 ohm current limiting resistor on the back of them, so they can be connected directly to 5 volt and ground. Each laser draws about 30 milliamps of current, so you need to ensure that your power supply here is capable of meeting that supply. I'm using a 500 milliamp 5 volt supply, so that's plenty good enough. And then those are all pointing at an array of corresponding light dependent resistors. Now the way that these are wired might seem a little bit unfamiliar to you, so I'm just going to try and explain this in more detail. What we want to do is we want to be able to read each of the values of these LDRs independently, but we're going to do that using only a single analog input pin by isolating each LDR in turn, creating a voltage divider circuit, and then taking a reading through this white wire here. So how do we do that? Well, what I've done is I've connected one of the legs of each LDR together. Those are all wired through to this shared line here, and that goes to ground on the microcontroller via this fixed resistor. Now this is a 1 kilo ohm resistor, but I'll explain how I got to that value in a moment. Now to read only one of these LDRs in turn and not let the others interfere in this circuit, what we're going to do is we're going to set one of these GPIO pins to output, and we're going to write a digital high signal to it. So what that means is on a 3.3 volt microcontroller like an ESP32, that will set this pin to be 3.3 volts. If you're using a 5 volt microcontroller like an Arduino, this will be 5 volts. So of the one light dependent that we want to read in turn, we have a high voltage across one of its legs. We then have the other leg connected through to ground via this fixed resistor here, and then we take an analog reading at the point between the fixed resistor and the light dependent resistor. Now to ensure that the other LDRs don't interfere with this reading, what we do is we set the pins that they're connected to as inputs. Now when you do that, what it does is it places them in a high impedance state. It effectively disconnects those light dependent resistors from the circuit, and they have no effect on the reading here. Once we've taken the reading from this top LDR, what we do is we turn that one off by setting its pin to input, and instead we then activate this pin as an output and write a digital high signal to it, and we take a reading from the second pin. And we do that in turn, iterating through all of the light dependent resistors, so we can take 5 analog readings using a single analog pin by connecting and disconnecting each LDR in turn from the circuit. Now, to explain how I got the value of that fixed resistor, so the way that light dependent resistors work is that as laser light shines on them, their resistance drops. So in a normal ambient light setting in a room, an LDR might have a resistance of about 10 kilo ohms. In complete darkness, that might go up as high as 100 kilo ohms or even higher. Whereas when the laser diode is shining directly on it, it falls to under 100 ohms. So what we want to do is create a resistor divider circuit where this value here can vary from 100 when the laser is pointing directly at it to upwards of 50,000, maybe 100,000 when it's completely blocked off by the light. The voltage that we read at this midpoint here is going to vary in proportion to the ratio between this variable resistance here and this fixed resistor here. So if we set this as a value of 1 kilo ohm and the LDR is at a resistance of 1 kilo ohm, at this point here the voltage will have dropped to exactly 50% of whatever it was when it started at the digital high signal. As the laser light shines on this, the resistance here falls, And that means that the voltage is going to increase red at this point in the circuit because a greater proportion is going to be dropped over the fixed resistor here. This now represents a greater proportion of the total resistance of that circuit. So you will need to do a little bit of empirical testing because depending on exactly where you install this and what kind of lighting you have in your room, you might find that the ambient light that you read across the resistors, and depending on the power of the lasers you use, I guess as well, you'll get different values read. But we don't need to get an exact reading. All we need to do is get a threshold value which we can be certain above or below which indicates whether the laser was pointing at the light dependent resistor, as in there was a hole in the key, or it was blocked from doing so. And in practice, I found that if you set the fixed resistor value to a kilo ohm and you set the threshold value you read at the analog read here to be half of the value that it's capable of reading, then that will give you a pretty good indicator or not of whether the laser is pointing at the resistor or not. So once you've taken your readings from your 5 LDRs, you've determined your 5-bit binary value, and then we're displaying the character that corresponds to that 5-bit binary on an LCD here. So this is a 128 by 64 pixel display. They're very commonly used for the controllers in 3D printers and things like that. They're also very easy to get hold of, and they use an SPI interface. So I'm using the master out slave input wire here. This blue one here goes to read write. The E pin, which is enable, goes to the clock pin of the SPI interface. And then the slave select goes to the DI pin of the LCD. So these are 3 of the SPI wires from your microcontroller. There is no information sent back from the LCD to the controller, so we don't need to connect the master in slave out or MISO socket. The only other thing we need to do is to power it. So even though an ESP32 runs at 3.3 volt logic, the LCD display requires 5 volts to actually energize the crystals in the display. So we connect VDD to the 5 volt output pin here. We connect the grounds together. The SPI interfaces, by the way, don't need to have a logic level converter. Even though the power for the crystals is running at 5 volt, 3.3 volt logic works on the SPI interface fine without any need to step it up to 5 volts. And these 2 wires at the end, the K- and the A+, these are the cathode and the anode for the backlight display. So the minus pin connects through to common ground again, and the anode pin I've connected through to 5 volts via a 220 ohm resistor. So that is that series limiting resistor, just to ensure that the backlight LEDs don't burn out. Again, on some LCD displays, rather like on the laser diodes, you might find that a series limiting resistor has already been installed, in which case this is actually not required. You can connect this straight through to 5 volts. And here's that same wiring laid out as a schematic. And here's the code that's running on the microcontroller. So I've written this using the Arduino IDE. It's not very long, it's only just over 100 lines long, and you can use this same code on an ESP8266 or 32 or any flavour of Arduino as well. So it's actually not very complicated, but we'll just step through it. Starting off at the top with some external libraries which I'm including, and the main one is this U8G2 library. This is a great, really comprehensive library for controlling all sorts of LCD graphics displays. So I'm using that to control my 128 by 64 character graphic display. We go into the constants. So these are variables that are going to remain the same for the duration of the sketch. I've declared a constant for the number of sensors I'm using, so these are my 5 lasers and the 5 corresponding LDRs. You can increase that value if you want, so long as you've got spare GPIO pins that can be used to select the LDR that you want to read from. And the number of unique patterns you'll be able to identify will be 2 to the power of however many number of sensors you have. So with 5 sensors, you're going to be able to get 32 unique combinations of readings. Now the next section, I've put in a little preprocessor define that is going to vary depending on whether I'm using an ESP32 or if I'm using another board like an Arduino. And the reason I've done that is not to do with the fact that ESP32s run at 3.3 volts and Arduinos run at 5 volt. That's irrelevant here. The reason I've put this in a if-def is because the ESP32 analog to digital converter chip runs at 12-bit resolution. So when you take an analog reading from one of the pins of the ESP32, you get a value that is between 0 and 4095. If you take a reading from one of the analog pins of an Arduino, that typically uses a 10-bit ADC chip, so you're going to get a value between 0 and 1023 instead. So if you want to write a single code base that you can deploy across different processors, you're going to need to adjust the value of the threshold that determines whether that LDR's got laser light falling on it or not, because the range of values you're going to get back from the analog read is going to be of a different factor. So that's the reason I've put those in different blocks there. You'll also see that I've defined different pins to use because the ESP32 typically has a different pin numbering convention from an Arduino. So this is my array of 5 pins that I'm going to select which LDR to read, and on an Arduino they're simply called 65432, and I'm also using one of the analog input pins, which are always denoted with an A before them. On the ESP32 it's got a slightly less obvious numbering convention if you're not used to them, so this is actually a range of continuous pins down the side of the dev board on one side, and then I'm using one more pin which is capable of reading an analog input. We've got our globals here, so I've got 2 global variables. The first one here is declaring a UHG2 variable. That is from that LCD display library, and it's got a rather complicated constructor here. The reason this looks tricky is because the library is capable of supporting lots of different sorts of LCD controllers. So here I'm using the ST7920 controller, which is the most common one I've found on these sorts of displays. This is the resolution of the display. I'm using the hardware SPI interface, and when you do that, you don't actually need to pass any particular pins into the constructor because it will use whatever the hardware SPI pins on your board are. So on an ESP32, the SPI pins by default are the master out slave input, well that's on pin 23, the clock line is pin 18, and the slave select line is on pin 5. If you're using an Arduino, the default SPI pins, well that's Mozzie on 11, clock on 13, and slave select on 10 instead. And so long as you're using those pins, you don't need to declare anything else in the constructor here at all. You can use these pin none definitions. Now, if for whatever reason you can't or don't want to use the built-in SPI interface that's using the hardware, you can emulate an SP interface using software instead, and that means you can use any GPIO pins. Now, if you want to do that, you'd use this constructor instead, and notice that it changes here to say it's software rather than hardware SPI interface. And if you do that, you do need to explicitly define in the constructor the pin that you've connected to the clock line of the LCD display, to the data line, and to the select line. And optionally you can define a reset pin as well. You don't actually need to use a reset pin specifically for the LCD display if you don't need to reset it in the code. I don't call the reset function here anyway. You know, if I wanted to reset the display, I'd simply reset the entire controller and power it off and on again. The other thing we keep track of is the last value. So this is a single byte value. Because we are storing 5 bits of data from our 5 LDRs, that can obviously fit into a single byte, and so long as you are using less than 8 lasers and 8 LDRs, you can fit that into a single byte. And that's going to keep track of the last pattern that was recognized, because we're only going to update the LCD display if we detect that that has changed from the previous reading. Okay, we go into the setup function. This is executed once when the code first starts running. We initialize a serial interface. That's just to use for debugging purposes to check the code is running as we expect it to. We start the SPI interface to the LCD display, and before we do that, I've just made one configuration change. Now, if you're using an Arduino, you probably don't need to worry about this, because the Arduino has a relatively slow processor speed anyway. But if you're using a more modern or a more capable processor speed, what you might find is it tries to push data to the LCD display faster than the LCD can actually process it. So the ST7920, which is the processor chip that is most commonly used in these LCDs, has a maximum refresh rate of 600 kilohertz. And if your ESP32, for example, is using the hardware interface, it might be trying to push data faster than that. So we explicitly limit the speed of the SPI bus interface here to 600,000, just to make sure we don't experience any screen glitching or tearing by pushing it data faster than it can cope with. And we initialize the pins we're going to use. So the LDR select pins, these are initialized as inputs, but we are going to, one at a time, change them to being outputs and write a high signal just to select each LDR in turn. And the LDR input pin, well, that's always going to be an input, because that's the thing that we're going to read at the midpoint of our resistor divider circuit to see the resistance of the LDR with the laser light shining on it. And then we go on to the loop function. So the loop function just runs over and over again for as long as the circuit is powered up. So the first thing we do is we initialize a new local byte val, and we'll initialize that as 0 to start with. And we're going to populate that value with the pattern of on and off bits that we read from each of the LDRs in turn. And that's what we're going to do in this section here. So we loop over all of our sensors, and then we have an inner loop that loops over them again, because what we want to do is we want to turn only one sensor on at a time, but we need to carry on through the loop to make sure that we've turned all the others off. So we count up through the numbers of sensors, and then we count through all the sensors, and we say, well, if the sensor we're looking at the moment is equal to the number of the sensor that we want to turn on, then we set the corresponding pin to be an output pin, and we write a high signal to it. So that is going to set the voltage at that pin to be a high voltage. That's 5 volts on an Arduino or 3.3 volts on an ESP chip. But for any of the other pins, so not the one that we want to look at the moment, we are going to set their pin to be an input. And that is going to enter this high impedance state. So it's effectively going to remove that LDR from the circuit. It's not going to have any effect on the reading that we take from the analog input pin. So we're going to loop over all of the sensors in turn, one at a time. We're just going to delay for 50 milliseconds after having changed those pin settings. I don't honestly know if that's actually required or not. But to me it would seem to be sensible to stabilize the circuit, because we've switched an input into an output and an output into an input, and just to wait 50 milliseconds to make sure that those have settled down before we take that sensitive analog reading at the ADC chip would seem to be wise to me. And then what we do is we do take our reading. So the LDR input pin that we defined at the top, this is our analog input that is going to measure the voltage halfway through the circuit that's connected through our variable LDR and our fixed resistor, and depending on the light that is falling on the LDR at that point, we'll be able to detect whether the laser was pointing at it or not. And we'll compare the reading that we take to the threshold value that we defined at the top, and that was one of these values that I said varied depending on whether we are looking at a 10-bit ADC or a 12-bit ADC. So a 12-bit has a greater range of readings, so we're going to have a higher threshold value. 10-bit only goes up to 1023, so we have a lower threshold value. But roughly speaking, we're going to set a threshold that's in the middle of the range of values that it's capable of reading. And if the measurement that we take at the midpoint of the voltage divider is less than that threshold, then we're going to write a 1 into our byte value for the corresponding bit. And if it's greater than the threshold, then we're going to write a 0 into that point. So we're building up a byte value starting from the right hand side, and we're going to write a series of 0s and 1s into the first 5 bits of that byte value. The far end byte bits are always going to be 0 because we initialize the byte here as 0. So a byte of 0 is equal to 8 bits, 0, 0, 0, 0, 0, 0, 0, 0, 8 times. But we're going to loop through them, and just for the 5 at the end, if the reading we get from the LDR is less than the threshold we defined, we're going to change the corresponding bits into 1s instead. And now we have a pattern of 1s and 0s, depending on whether the LDRs were exposed to the lasers or not. Now, this closed bracket here, this signifies that we're at the end of the loop where we went through all the sensors. So we have taken our reading, we've got our byte value, and now we can do something with it. The first thing we're going to do with it is going to see whether the value is equal to 0. Now, if the value is 0, what that means is that every one of the LDRs detected light shining on it. That made that their resistance dropped, and it means that the voltage that we read at that point was higher than the threshold. So that either means that there was no card present at all, and all of the lasers just shone directly onto the light dependent resistor below them, or that a card was inserted but that it had got holes in all of the positions. So this is the example I demonstrated where I had the rotary disc that I was rotating through, and I mentioned that the last slot after the message had been encoded, I made holes in every single one of the positions. This is when that case would get activated, and what it does is it clears the buffer. So it's like a reset command essentially when the value is 0. Otherwise, if the value has any non-zero value at all, well, what we'll do is we'll print to the serial monitor first of all what value that is. That's going to be very helpful in your debugging, so you can actually see what combination of the LDRs have been activated or not, to make sure that your lasers are pointing in the right direction and the things you're expecting to be activated have been. And then what we'll do is we'll print the character that corresponds to the bit value, the number of the bit value, onto the LCD screen. So we'll choose a font that we want to write it in. You can go to this web page here and see the big list of fonts that is supported by the U8G2 library. There's all sorts of different sizes. You can get bold and italic and different fonts. So I'm choosing a nice large font. It's 49 pixels high. I'm going to move my cursor to be approximately centered in the display. So it's going to be 46 pixels across, 60 pixels down. And then I'm going to print the character that is whatever value, whatever byte value we read from the sensors. I'm going to add 64 to it and then print it to the LCD. Now the reason for doing that is that the U8G2 library uses the ASCII character set. So the ASCII character set, which is used in all sorts of computer programming languages, in which a letter A is the number 65 in that character set. And then B is 66, C is 67, they count up. So I've got a value here that is non-zero. I know it's not 0 because 0 was done up here, and that was my clearing out case. If it's the value 1, then I want that to correspond to an A. So what I do is I add 64 to it. That gives me the number 65. I then convert that to a character, so that's going to be the letter A, and I print that to the LCD screen. Now, actually, I tell a lie, it doesn't quite print it to the LCD screen. What it does is it prints it to the buffer. So this command here doesn't immediately send it to the LCD. What it actually does is it's generating an in-memory copy of that we want to display on the LCD screen. To send that data to the LCD, we call the send buffer command, but we only call that if the value is different from the last value. So let's say you've inserted a card with the letter A, and so val is going to be equal to 1. Each time we go through the loop here, we don't clear the buffer out because we've got a value. We come into this section instead, we work out that the letter corresponds to the number 1, which is an A. We print an A into the buffer, but there's no point sending it to the LCD if it's the same as what the LCD is already displaying. That would just be an inefficient data transfer. So only at the point that the value we're reading is different from whatever the last value was, we'll send the buffer, and that buffer will contain either the new letter corresponding to the value that's been read, or it will simply be an empty buffer if the card was removed or if the card had spaces in each of these slots there. So that's going to clear the display. And the last thing we do is we update the last value with whatever we read this frame so that when we next go through this loop, we can see whether the value has changed again. And that's it. Now, I think one of the things I like about this project is it's got this strange juxtaposition between high-tech and low-tech. On the one hand, you've got lasers and LCD displays and quite advanced microprocessors that are pretty modern. And then on the other hand, you've got really quite simple, plain wooden discs and cards. And in fact, these are quite evocative of the way that data would have been encoded in a vinyl record or in punch cards. And I think that this means that you can actually do a lot to style this in different themes. These can be plain wood as they are here. You could make these out of acrylic. You could fashion them to look like stone tablets. And you could hide as much of the electronics here as you wanted. There's no reason to have the LCD display at all. That's really for debugging, so I could show you the values that were encoded in each of these discs. But what you could do instead is simply use each of these cards as a unique identifier and then make anything happen in the code you wanted when that card had been recognised. Now, as always, I will upload the code that I've demonstrated and the wiring diagrams over to my Patreon account, and I will put a link in the description below. So if you'd like to download that, or for any of my other escape room projects I've shown on this channel, please do head over there. If you are unable to or simply don't want to support me, that's not a problem. I will continue uploading these tutorials each month to YouTube for free, and you can always subscribe to this channel to find them here anyway. In the meantime, if you have any questions about this project, or if you've got any comments, ideas, or if you end up using this in an escape room, I'd love to know. So please do tell me about it below. And otherwise, I just want to say thanks very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.